High-density catfish farming operates on a razor's edge. Thousands of fish packed into commercial grow-out tanks depend entirely on constant water recirculation. Preventing biological collapse requires mapping the exact flow of water and oxygen using abstract transfer matrices. But when engineers run these fluid simulations on computers, the math frequently shatters. The matrices mapping the water flow disintegrate into chaotic hardware noise. Mathematicians call this the numerical killing zone. On a finite computer grid, precision collapses and observable data turns to useless static. Standard theoretical models fail this test entirely. However, a matrix based on a real-world physical system easily survives. It is the Recirculating Aquaculture System, or RAS, Ulam operator. In this model, physical design saves the math. A rim inlet jet forces continuous, high-volume water throughput across the bulk mixing core directly into an off-center drain. This relentless flow prevents the matrix from stalling across tested grids. The operator safely navigates the numerical killing zone. But a stable matrix on a computer monitor does not automatically guarantee the physical survival of the fish in the tank. To bridge the gap between abstract computer grids and living fish, engineers use a finite-grid diagnostic called the geometric mixing penalty, or DGM. This equation calculates the penalty. DGM divides the maximum support ratio, representing the well-mixed core, by the minimum support ratio, which flags poorly mixed regions. This numerical penalty, extracted from the grid itself, measures how broadly flow states are observable across the tank. When the DGM penalty grows, it flags the exact severity of the tank's dead zones. It gives engineers a precise mathematical measure of how much longer a toxic chemical spike will hide from their sensors. Out on the commercial floor, the biology forces a ticking clock. High-density African catfish pack the grow-out tanks, consuming oxygen and producing ammonia at staggering rates. This diagram illustrates the biological reality. If a pump fails, dissolved oxygen plummets to lethal levels in exactly 10 minutes. Static wall probes monitor clean currents, remaining entirely blind to rapid oxygen drops unfolding inside the tank's sluggish dead zones. Facilities deploy mobile robotic sensors to physically swim through these dead zones. The primary engineering challenge is calculating exactly how fast that robot must complete its patrol. To prevent a kill-off, the biological 10-minute countdown and the DGM penalty must combine into a rigid speed limit for the mobile fleet. Engineers enforce this speed limit using the safe revisit heuristic. This equation defines the heuristic. You take the 10-minute critical time for dissolved oxygen and divide it in half to build in a strict safety margin. Then you divide that result by the DGM penalty. This calculation ensures that even if a sensor is swimming through the absolute worst dead zone, it completes a pass fast enough to catch an excursion before the water turns lethal. But finite grid mathematics rarely scales smoothly. When engineers ran this simulation at a specific grid resolution of 128, they hit a severe anomaly. This line graph tracks the metric's performance across different resolutions. At exactly 128 grid cells, the boundaries interact awkwardly with the off-center drain. This geometric clash creates a massive dead zone artifact, causing the DGM penalty to wildly spike up to 1.223. Looking at the data table below, you can see the physical consequence. Because that penalty spikes, the heuristic formula slashes the allowable time frame. The maximum revisit time for a mobile sensor gets squeezed down to barely 4 minutes. You cannot write off that spike as a simple resolution glitch and smooth the curve. In an industrial RAS tank, that anomaly is a deadly, worst-case scenario that dictates physical operation. To handle these unpredictable grid anomalies, engineers operate under the Supremum Safety Protocol. This protocol mandates that you never derive your safety limits from a single grid resolution. You must run an entire ensemble of grids, find the absolute worst mixing penalty among them, and build your entire safety factor on that exact number. Applied to high-density catfish, the oxygen timeline is too tight. A mobile robot cannot patrol fast enough to clear the 4-minute limit. Mobile units are strictly restricted to sweeping for slower ammonia risks, while continuous static oxygen probes remain absolutely mandatory. Finite grid mathematics is discrete, imperfect, and full of anomalies. But when you stop trying to smooth over its flaws and instead apply rigorous discipline, those grid limits become the exact boundaries keeping thousands of living things alive.